We're going to start talking about one-to-one and onto functions, and then move on to linear transformations. Let f be a function from a set x to set y. F is called one-to-one or injective if and only if for all elements, like x1 and x2 in set x. If y values are equal to each other, then you can conclude that x values are equal. Equivalently, if x values are different from each other, you can conclude that y values are different from each other. Symbolically, function f that maps x to y is one-to-one if and only if for every x and y in the domain, if f of x1 is equal to f of x2, or if the output values are equal to each other, then you can conclude that input values are equal as well. We say that a function is onto or surjective if and only if, given any element y in y, it's possible to find an element x in x with the property that y is f of x. Symbolically, if f maps x to y, it is onto if and only if for every y in the codomain there is an x in the domain such that f of x is equal to y. So this is an example of one-to-one linear transformation, and this is not a one-to-one linear transformation. Here, x1 and x2 are different from each other, but their output values are the same. So this is not a one-to-one linear transformation. We have a nice theorem. Let T from B to W be a linear transformation. Then T is one-to-one if and only if the kernel is equal to a single value 0. So if your kernel just includes the 0 vector, for sure you can say that, hey, we have a one-to-one linear transformation. Remember that if T from n space to m space is a linear transformation, that Tx is equal to Ax, then the kernel of T is equal to the solution space of Ax equal to 0. Also remember that if A is an m by n matrix, then the set of all solutions of homogeneous system of linear equations Ax equal to 0 is a subspace of Rn, which is called the null space of A, and is denoted by n of A. And n of A is equal to the set of all vectors in the domain such that Ax is equal to 0. The dimension of the null space is called the nullity of A. So we are going back and forth between matrices and linear transformation because, as we saw before, there's an important connection between them. So to prove the theorem, first assume that T is one-to-one. If T is one-to-one, then T of V equal to 0 can have only one solution V equal to 0. There is no other option. So the only value that can make TV equal to 0 is V equal to 0. So since T is one-to-one, the equation TV equal to 0 has only one solution, 0. Conversely, if kernel of T is equal to 0 vector and TU is equal to TV, since T is a linear transformation, T of U minus V is equal to TU minus TV. But since TU is equal to TV, it means that the difference between these two is equal to 0. So what's the meaning of that? It means that U minus V is in the kernel of T, and it must be equal to 0. So we just showed that U is also equal to V. It means that T is one-to-one. So again, to prove this theorem, T is 1 to 1 if and only if kernel of t is equal to 0, we have two ways. First, we show that if t is 1 to 1, then the kernel is equal to 0. Then we show that if the kernel is equal to 0, we have a 1 to 1 linear transformation. If t is 1 to 1, tv equal to 0 has only one solution, v equal to 0. So kernel of t includes only one member, which proves the other side of the theorem. If kernel of t is equal to 0, and you set output values equal to each other, you should be able to show that input values are the same as well, but we have to do a little bit of algebra. Tu is equal to tv, but t of u minus v, going back to the definition of linear transformation, is tu minus tv, which is 0, because they are equal to each other. The output values are the same, but it implies that the vector u minus v is in the kernel of t. So it must be equal to 0. So u must be equals to v, which means that we prove that if kernel is 0, t is 1 to 1 as well. So we just proved this theorem. If t is 1 to 1, if and only if kernel of t is equal to 0. Now let us go back to the linear transformation that takes every vector, and it basically gives you the transpose of that vector, transpose of that matrix. In this case, when we're talking about vector, we're talking about matrices. This is a 1 to 1 linear transformation. Why is that? Because we just showed that the kernel only consists of an m by n 0 matrix. The only solution to t of a equal to 0 is 0. There is no other option. So since the kernel is equal to 0 vector, it means that for sure you can say that this linear transformation is 1 to 1. So on the exam, if I ask you to write me an example of a 1 to 1 linear transformation, you're going to say, hey, here we go. This linear transformation that maps the vector space of m by n matrices to the vector space of n by m matrices, that takes every matrix and gives us the transpose of that matrix, is definitely a 1 to 1 linear transformation. Again, why is that? Because the kernel is always equal to 0 matrix. There is no other solution here. Remember the 0 transformation. 0 transformation takes every vector and it gives you 0 vector back. This is not a 1 to 1 linear transformation. Why is that? Because the kernel is not 0. As you remember, the kernel is all of the domain. The kernel is the space itself. So since it doesn't satisfy this condition, it is not a linear transformation. As easy as that. So again, on the exam, if I ask you to write me an example of a linear transformation that is not 1 to 1, you simply say that, hey, 0 transformation is the example that you're looking for.